Swayam Prabha. Digital India. Educated India.
Hello friends. So, in the previous lecture we have discussed about the discrete Fourier transform algorithm and using full cycle DFT algorithm how we are able to obtain the phasor value of the sampled values available for any given signal. Now, in that class we have discussed regarding the equation of DFT, that is x of k is equal to C sigma x of n e to the power of minus j 2 pi by n k n, and if we represent this equation in matrix form, then it is on left hand side we have the phasor value of different harmonic component like DC value, fundamental and so on, and on right hand side we have some constant C, then weight matrix and then the sample values, and CW and SW are given by these two equations, that is cos or sin 2 pi by n k n, and when we further multiplied this, finally we obtain the value of the ICW and ISW. So, to understand this, let us consider one example of full cycle discrete Fourier transform algorithm. So, consider a signal which has 50 hertz fundamental frequency and this signal is acquired with a sampling frequency of 800 hertz. In this case, we wish to calculate DC component, first fundamental term, third harmonic and fifth harmonic from the available sampled values of the signal, and we want to calculate phasor value of DC first, third and fifth harmonics. So, the available samples of the acquired signals are given here in this table. So, here you see the first row indicates the sample number where 16 samples are shown. So, we have a sampling frequency that is 800 hertz and we have the fundamental frequency of the acquired signal, that is 50 hertz. So, number of samples in a cycle, that is capital N, is given by Fs by F0. So, that is 800 by 50. So, it comes out to be 16 samples in one cycle. So, that is why the sample number that is given from 1 to 16. The value, let us say when we acquired first sample, the value of that, let us say current quantity is 14.1. Similarly, when you acquired other samples up to 16, the values are also shown in the second row. Now, let us start with the calculation of phasor value of DC term. So, this term is nothing but we have to understand or put the value of k, that is 0. So, our original equation on left hand side, that starts from x 0 to x of k, that is equal to C, and we have weight matrix multiplied by sampled value matrix. Now, let us first calculate the unknown terms of the weight matrix, that is CW and SW. So, we know that CW is given by cos of 2 pi by n k n and SW is given by sin of 2 pi by n k n. So, as we have 16 samples per cycle available, and to calculate the DC term, as we have discussed that we have to put k is equal to 0 and small n, which is a sample number that varies from 0 to 15. So, total 16 values. So, let us see how we can calculate this CW and SW term. So, we have the value of n, that is from 0 to 15, it varies. At each sample we have the values of I n from 0 to 15, and C w, if you put the value of k that is 0, capital N that is 16, and small n that is again if you vary let us say 0 to 15, then you know that the value of k is 0. So, cos of 0 that is 1 for all the samples, and similarly the value of S w, if you put capital N that is 16, k that is 0, and n varies from 0 to 15. So, S w comes out to be 0. So, as C w that comes out to be 1 and S w that comes out to be 0. So, you can easily now calculate the values of this weight matrix after multiplying with this sampled value matrix. So, here we have already calculated the value of C w and value of S w. So, here now we have to multiply this first row with the sampled value of the matrix. So, let us multiply this 2. So, when you multiply this 2, so C w has to be multiplied with I n. So, you have to multiply this term with this. So, it comes 14.1, similarly 9.2 with 1. So, this 9.2 and so on, you can have the last value that is 14.9. And similarly, you can also have the imaginary term S w, which is nothing but the multiplication of S w with I n. So, as the value of S w is 0, so your value of multiplication of I n with S w that comes out to be 0. And if you take addition of all these terms I n into C w, that comes out to be I c w equal to 32, and if you add I n into S w, all the terms I s w comes out to be 0. So, this comes out to be I c w equal to 32 and I s w that is equal to 0. Now, we obtain this term. So, only thing remaining that is we have to multiply it with value of capital C, and we have discussed that when we have DC value, the value of C is given by 1 by n. So, x 0 that is the phasor value of DC term, that is C into this I c w minus j I s w. So, C is 1 by n into we have already obtained 32 minus j 0, this is your I c w and this is your I s w. So, you will have the value final 2 angle 0. Now, let us calculate the value of phasor of the fundamental component. So, here for that we have to use k that is equal to 1. So, when we have the value of n varies from 0 to 15 and we have I n already given for each sample, then C w for k equal to 1 you can have the value like this. So, simply you have to put C w is equal to cos 2 pi, capital N is 16, k that is 1 and n you have to vary from 0 to 15. So, if you put this value here in this equation, then you will have the value of C w that is 1.9 and up to 0.9 last value. Similarly, you can have the value of S w. So, here you can put let us say this value, we have sine of 2 pi, capital N is 16 into k is 1 into n that is 0. So, sine 0 that is 0. So, you will have this term. Similarly, this term that is constant term which is going to change, that is your sample number. So, if you put this value here for each sample, you will have the value of S w also. Once you have the values of C w and S w for k equal to 1, you can multiply this C w with I n. So, you will have this C w into I n, that is this value. You will have again this I n into C w. So, you will have this term. Similarly, you can have the multiplication of this term and finally, you will have the term that is this one. Same way, you can also calculate I n into S w by multiplying I n with the SW. So, you will have the values of In into Cw and similarly you will have the values of In into Sw. You add all these values here. So, you will have ICW is equal to 80 and you will have ISW that is 0. So, here if you put x1 which is the phasor value of fundamental term k equal to 1, that is C into ICW minus JISW. So, other than DC component the value of capital C is 2 by n and this value you have obtained, that is 80 and this value that is 0. So, you can put it here. So, you will have the fundamental term phasor that is tan angle 0 degree. Now, similarly let us calculate the phasor value of third harmonic component. So, we have to put the value of k that is 3. So, if we put the value of k that is 3 here, then you have Cw term that is equal to cos of 2 pi by n, that is 16 into k, that is 3 into n. So, n we are taking first sample, that is 0. So, cos of 0 that is 1. So, you will have this value and this is also SW that is 0. Similarly, you can have the other values by varying the value of n and you can put the value here in Cw and you can put the value in the equation of Sw and you will have the value of this term, that is Sw, and you will have all the values of Cw for different value of small n. Now, once we have the values of Cw and Sw for k equal to 3, you can multiply this Cw with In and you can multiply Sw with In. So, when you multiply this Cw with In, you will have the value this. Similarly, you will have the value that is this. Same way you can have the value of In into Cw and you have the value of In into Sw. Then you add all these term. So, you will have ICW is equal to 17 and you will have ISW that is equal to minus 17. So, if you put x3 phasor value of third harmonic, that is capital C 2 by n into 17, that is your ICW minus j and ISW is minus 17. So, finally, you will have the equation this 2 by 16 into 17 plus j 17 and finally, you will have the value 3 angle 45 degree. Similarly, if I want to calculate the fifth harmonic component phasor, then we have to put the value of k, that is 5, and similarly you have to calculate the value of Cw and Sw using the equation cos oblique sin 2 pi by n into kn, and then you have to multiply that Cw with In and Sw with In and you have to add it. So, finally, you will have ICW and ISW value that is 0 and minus 8 respectively. So, if you put here x of 5, that is phasor value of fifth harmonic component, that is 2 by n. So, 2 by 16 into 0, that is your ICW, and minus 8, that is your ISW. So, you will have the value 1 angle 90 degree. So, whatever samples we have taken and whatever the different phasors we have calculated the phasors, that is x of 0, x of 1, when x of 3 and x of 5, and this is your DC term, right. This is your fundamental term and this is your third harmonic and this is your fifth harmonic. So, whatever values we have obtained, phasor values of the signal, that signal looks like this. So, this is your DC term, that is 2, then you have fundamental term, that is 10 angle 0, then you have the third harmonic, that is 3 angle 45. So, 3 into cos 3 2 pi f 0 t plus pi by 4, and you have fifth harmonic, that is you can see here it is 1 angle 90 degree. So, you have 1 and angle that is pi by 2. So, the signal which is shown here in this equation A, that if I plot, then it looks like this, and what we have done in this signal, that is IT signal, we have considered one cycle window and in one cycle we have taken 16 samples and then we have estimated the phasor value of this term, that is DC term. Then we have seen this is our fundamental term, then we have third harmonic term and we have the, this is your third harmonic and we have the fifth harmonic term we have estimated. Now, if I want to implement this algorithm in terms of code, let us say in C or MATLAB, then how we can do it. So, the flow chart for implementation of this full cycle DFT is shown here. So, here initially you have to enter two values, one is the sampling frequency Fs and another is the fundamental frequency, it can be 50 hertz or it can be 60 hertz. Once you have the value of F0 and Fs, you can calculate the number of samples per cycle, that is capital N by Fs divided by F0. Once you have this, you have to enter the value of k, that is harmonic number. So, let us say you enter the value of k, that is 0. So, that means you want to estimate the phasor of DC term, or if you enter k, let us say 3, then you want to estimate the phasor of third harmonic. So, for that you need to enter the value of k. Then we have to define the one matrix, that is let us say IT matrix, and that size of that IT matrix is nothing but the 1 cross n, where n we have already obtained, we have already defined. So, n is the number of samples in a cycle. So, let us say n is equal to 16, then the size of this IT, that should be 1 by 16. Now, what we want to calculate this weight matrix. So, for that I have to initialize the sample number n, that is 0, and I have taken another variable, let us say p, that starts from 1, and then I put the matrix IT, that is 1 comma p. So, p that is going to vary, initially it is 1 and then it increases from its original value to the next value, that is p is equal to p plus 1. So, here you can see the value of this CW you can obtain by cos 2 pi by n k n, and value of SW you can obtain by sin 2 pi by n k n. So, here similarly for in first row, if you have let us say 16 samples in a cycle, then you have to start with 1 0. So, let us say 1 is your k value and you have to start this n with 0 and you have to go up to 15. Then you have to end when your p is equal to n, and when it is equal, then the next task is you have to collect the sample data of one cycle duration for another matrix, let us say the X matrix, and the size of that matrix is n cross 1, and that is nothing but here 16 by 1. So, this value of X, that is nothing but the matrix of sample values. So, once you have this, you have to multiply this X matrix with IT matrix, and then finally you have to multiply with capital C, which is fixed. For DC it is 1 by n, for other it is 2 by n. So, finally you will have the value of phasor for a particular value of k which you have entered. And then in moving window, if you want to take next sample and if you want to discard the previous sample, then you have to move it here and you can calculate it and you can use this phasor value for any further application. Now, after this discussion, let us see what is the aliasing error in phasor estimation. So, when we have a frequency component available in the acquired signal which is greater than Nyquist frequency, then this effect plays an important role. So, we know that we have discussed earlier also that according to Nyquist criteria, the maximum number of frequency, let us say NF, whose phasor can be accurately estimated by full cycle DFT, that is calculated by the equation, that is NF is equal to Fs by 2 by F0. So, let us consider the sampling frequency in earlier case which we have considered, let us say 16 samples per cycle. So, let us consider my sampling frequency is 800 hertz. My F0 will be, let us say, 50 hertz. So, if I use this value, then your NF comes out to be 800 by 2 divided by 50. So, this is nothing but 400 by 50. So, this comes out to be 8. So, that means when NF is equal to 8, this indicates that the maximum number of frequency, that is NF, that implies the order of frequency that is to be calculated. So, if your NF value is 8, then you can calculate the maximum order of frequency only up to 8, and normally it starts with 0 because we have to calculate DC value, and it will go up to 7. So, if you add this, you will have the value of NF, that is 8. So, that means when NF is equal to 8, then the order of frequency that can be calculated, that is from 0 to NF minus 1. So, 0 to 7, that becomes 8. So, if the original signal contains harmonics which is greater than your NF which we have calculated, then the energy of this higher order harmonics that is going to reflected on the lower order harmonics, that is in between 0 to NF, and this effect is known as aliasing effect. So, because of the presence of this NF plus mth harmonic term, NF minus mth harmonic component will be affected. Now, to understand this, let us consider our Fs is equal to 800 hertz. So, F0 that is equal to, let us say, 50 hertz. Your number of samples in a cycle, that is 16 Fs by F0. So, NF comes out to be, as we have already calculated earlier, it comes out to be 8. So, let us say NF is equal to 8, which is Fs by 2 divided by F0. So, the meaning is, if we are acquiring, let us say, some signal, say if we are taking samples of the signal, and if that signal contains, let us say, 10th harmonic. So, 10th harmonic of the fundamental, that is 50 hertz, that is nothing but 500 hertz. We have already discussed that the sampling frequency according to Nyquist criteria, that is greater than 2 times F max. So, my F max is 500 hertz. So, my sampling frequency should be greater than 1000 hertz if I want to avoid aliasing error. But here you can see the sampling frequency is 800 hertz, the signal which we are acquiring, it contains the 10th harmonic component. So, in that case what will happen, your NF plus mth harmonic. So, let us say 10th harmonic is present, that is equal to your NF plus m. So, 10 is equal to your NF, that is 8 plus m. So, here you can say your value of m, let us say that is 2. So, NF minus m. So, if I consider NF minus mth harmonic, then that comes out to be NF is 8 minus m is 2, which we have calculated. So, 6th harmonic is affected. So, when we acquire any signal, and for that signal, if sampling frequency is not going to follow Nyquist rule or criteria, and if that signal contains the frequency component which is higher than NF, then the, let us say, if we are having or 10th harmonic component present in the acquired signal, then because of that 10th harmonic component, your estimation of 6th harmonic, that will be affected. So, to understand this, let us consider a signal IT which is sampled at 400 hertz. So, when you sampled at 400 hertz with fundamental frequency, that is 50 hertz, your NF comes out to be 4, that is 400 by 2, 200 divided by 50. So, that comes out to be 4. Now, let us say this IT is a combination of this equation. So, that contains, let us say, 10 cos 2 pi f t plus third harmonic 3 cos something plus 3 cos 7. So, it contains 7th harmonic also. Now, as the number of samples in a cycles are 8, so we have 8 sample and we are going to acquire the value for each sample. Now, here as the value of n, that is number of samples in a cycle, 400 hertz is the sampling frequency. So, n comes out to be 8, and let us say k is equal to 1 for fundamental. So, if you calculate the value of Cw and Sw as we did earlier by putting the value of k, that is 1, n varies from 0 to 7 and capital N, that is 8, in the cos of 2 pi by n k n equation and sin of 2 pi by n k n equation, you can have the values of Cw and Sw. You multiply I n with Cw and I n with Sw. So, finally, you will have the value of ICW, that is 52, and you will have the value of ISW, that is 0. So, your x1 term, that is k is 1. So, fundamental phasor of fundamental term, that is C into this equation. So, that comes out to be 13 angle 0. Similarly, you can calculate the another component, let us say the phasor of third harmonic, and you can have the value, that is 3 angle 45. So, our original equation IT is this, right. So, you can see the estimated value of fundamental term, that is 13 angle 0, whereas in the actual signal of IT the fundamental term present, that is 10 angle 0. So, that means because of the presence of 7th harmonic in the signal, the effect is going to occur on the fundamental component, and fundamental component is wrongly estimated. So, as 7th harmonic is present in the signal, so NF plus M, right, that is nothing but your 7th harmonic. So, 7 is equal to NF plus M, NF is your 4. So, M comes out to be 3. So, 7 is equal to NF plus M, NF value is 4. So, M value that comes out to be 3. So, hence the affected harmonic, that is NF minus M, that is 4 minus 3, that is fundamental, and that we have observed that we obtain 13 angle 0 phasor value of fundamental instead of 10 angle 0. So, if I consider, let us say, different value of sampling frequency, here I have considered two sampling frequencies, in one case 400 hertz, in another case 800 hertz. Fundamental frequency I have considered same, that is 50 hertz, and accordingly if I calculate, NF comes out to be 8 and 4. So, if I consider, let us say this case, second row, then in this case you can see that the number of harmonics present, that is 0, 1, 3, 5th and 11th, and your NF value is 8. So, as NF is 8, so it can only estimate the frequency order from 0 to NF minus 1, that is 7. So, as 11th harmonic is present, so your M comes out to be 3, right, that is 11 minus 8, that is 3. So, definitely the term which is going to affected, that is this 5th harmonic, it is going to affect. How this comes out to be? This comes out to be, this is nothing but your NF minus M. So, M comes out to be 3. So, NF is 8. So, 8 minus 3. So, 5th harmonic gets affected. Similarly, let us consider this case, that is second, where the number of harmonics present, that is 5th, 7th, 3rd, 1st and DC value, NF is 4. So, here you can see the value of M, because as the value of NF is 4, so it can estimate only up to 0 to 3rd harmonic, but here 5th and 7th are also present. So, because of 5th and 7th, you can see that 5 minus 4, that is 1st, and again 7 minus 4, that is 3rd, means when you estimate 1st and 3rd harmonic, then both phasor values are affected because of the presence of 5th and 7th harmonic. Similarly, if you consider this case, then here you can see the 8th harmonic is present. So, your value of M comes out to be 8 minus 4, that is 4, and again NF minus M, that is 4 minus 4, that comes out to be 0. So, DC value gets affected. So, that means whenever we have any higher order harmonics are present, that is greater than NF, then its effect will be reflected on the estimation of other harmonic components. So, in this class we have discussed initially with one example that how to calculate the weight matrix, that is CW and SW. Then we have also discussed how to calculate ICW and ISW, and then we have finally discussed that how we can calculate or estimate the different phasors, let us say 0, 1st, 3rd, 4th, 5th harmonics. And then we have discussed an important effect of the aliasing error, and we have discussed that if the number of harmonics present in the acquired signal is greater than NF, then the effect of those harmonics are reflected on the phasors which we are going to calculate. So, thank you very much.